So in lecture 45, we're going to begin heading now down the axial combinations that we put together using our new axial combination theorems derived from Euler's formula and the law of cosines for spherical triangles. The first case is a 2, 2, 2, and we're just going to add extenders, which moves us down on our column in our table that we were creating. And um, we're going to go through, in this case, each of the combinations. So we're going to say, all right, I'm going to go down and add a horizontal plane. I'm going to add a mirror plane. Now, it turns out that there's only going to be two new crystallographic groups from the four elements that we're going to add. In this example, I'm going to do all of them just to show you how it works. But then in future lectures, we'll only cover the cases that actually produce new crystallographic groups, and we leave it to you, the student, to derive the other cases that end up not being important because either they're duplicates or they're non-crystallographic. Okay, so the first one is the horizontal plane. So first, just to remind you about where we are in 222, recall that the 222 case, this is just for, that's a very bad sphere, but anyway, just to give you the case that we're starting off with, is if you recall, these up elements were there, the down elements are here, and in the stereographic projection of the symmetry elements, we had a situation like this. So we had twofold axes that are running here and here and then into the plane of the paper. And that's it, actually. There are no mirror planes, so it's a little confusing because when you see these things, these are axes and not mirror planes. You can see that a little more easily over in the motif because you see here that this is the twofold axis that ends up relating this guy to this guy, this guy to this guy. But then if I look down this direction, right, or this direction, I have twofold axes that are relating these to each other as well. So clearly when we add, you can believe that there's going to be some combination of mirror planes that will change the situation and make this into a new point group, especially since all we have is something on the front connected to something in the back and vice versa on a twofold axis with other twofold axes as well. So let's look at adding the horizontal mirror plane first. It's clear from adding a horizontal plane here. Let's add the horizontal plane here. So that's in the plane here. And you can see immediately what that does. That just reflects this guy onto the other side, this guy onto the other side, and then the other two onto the front side. So let's think about what that actually is now. If I look at it, I realize that I have mirror planes along all perpendicular to all twofold axes. So if I look here, certainly I have a mirror plane relating this to this. So it's kind of a mirror plane, going around there, right? And then there's a mirror plane obviously here, so I have a mirror plane, going there. So I end up with mirror planes actually perpendicular to all axes, which gives us the name of this one. It's 2 over m, 2 over m, 2 over m, because in each twofold axis, I end up having, around the great circle perpendicular to that, I end up having a mirror plane. So again, remember how to picture these things. If I looked, down on this, I would see that there's a mirror plane reflecting this. It's a 2mm type of on each, and when I look down each axis, right? That's actually a good way to look at this one. This is actually sort of a 2mm looking down each one, except that remember that the horizontal mirror planes, produced it. Okay, so that's why what I have in each direction is a twofold axis with a mirror plane perpendicular to it. Now, that brings up an interesting thing, because recall, if I have a twofold axis and I have a horizontal mirror plane, that means I get an inversion center. So that means that there's actually an inversion center in there as well. Each one of these twofold axes passes through, and I have these mirror planes. Passing through with that inversion in the center. It's called 2 over m, 2 over m, 2 over m. Okay, let's think about the, and remember in the other case when I just had 2 over m without anything else, remember this implied an inversion center by definition because of this. Same thing here. So if we add a vertical plane, it turns out that nothing is different. So just to show you that quickly, so we don't have to waste too much time here. Again, if I look at our original motif, if I add a vertical plane now, which, in a way is looking down, from the eye point of view, what you start to realize is that that actually isn't too much different from looking down the one we're looking down now. It's just that these are moved further apart, right? So whether I look down this direction or whether I look down the other direction, it's going to look kind of similar, because the only difference is that I'll have these two on the front side, these two on the back side, right? But once I put the mirror plane in, vertically, right, it's going to reflect this guy across. So it's going to produce a green circle on the other side, and this is going to produce a red circle, and same thing down here. It's going to produce red circle there. And green circle here, and that's going to mean that we actually have mirror plane going across that circle as well. So this is not a unique case. You still end up with 2m, 2m, 2m. Now, this is the first time we're going to apply a new extender here, where we're going to say, all right, let's take our case. And, if we draw the element for the 2, 2, 2, we had a twofold on each direction because we had a series of twofold axes going in every way 2, 2, 2. Now, we've added mirror planes across and up and down, and it gave us the same answer. But now, we have the opportunity to actually add a mirror plane through here. This is a good example of a diagonal mirror plane. Or on this sphere, in other words, there's a plane, there's a great circle, right, cutting through over here. Okay? So to see that a little bit, we can draw just that same plane, if I can do it well, across here. And that's going to reflect this one across here, if I can do this accurately. And it's going to reflect this guy across there. And if I draw this correctly, it's skewed, but I know what the answer is supposed to be. So obviously I didn't draw this symmetric, but this reflects across there, that reflects across there. And same thing with this guy. This guy reflects across here. And this guy gets reflected across here. And you can see a couple things right away, which is not surprising from other theorems that we had. If we have a mirror plane that way, we're going to have a mirror plane this way. Remember the twofold act. Oops, sorry, I should pick a different color. Remember 2mm essentially, 2mm formula. And you can see that is induced very easily here because it's obvious that with that one reflecting plane, I create another one here, another one here that reflects across this way too, right? So really the signature of the diagonal plane on the 2, 2, 2 is that I have this couplet here, and I have the rotated couplet 180 degrees over here. But then in here and here, if you look at it, if I only rotated 90 degrees, it's the inverse of it. Okay, it's the inverse of this, because notice how if I rotate over here, the red would go on the green, so that's not correct, right? So you have the mirror image of the couplet on the two sides, but there's two diagonal mirror planes going through the center. Now, if you look at that, you should recognize immediately then, aha, that is the situation 90 degrees away, but inverted, that's the same as the 4 bar, right? Remember how you can imagine now taking this couplet or looking at each one individually, it doesn't matter, but I can rotate it, over, right? And then, I'd have a red here and a green over here, right? And then what happens is I put them through an inversion in the center, right? And I would pop out on the other side with red and green over here, right? Because I have the inverted set. See, it won't work with this one with the inversion center, because if I go through here, I'd have green to green, right? So the roto inversion is required, not a regular inversion. So what that means is that not only do I get these mirror planes, but it transforms this into a roto inversion axis. Right, so we have the roto inversion symbol in the middle, and we have mirror planes running along here and here. So that's, now we got to make our nomenclature. Well, clearly I have in one axis direction, I've got the 4 bar, right? So that's pretty easy. And then if I look in the other directions, I essentially have twofold axes with mirror planes. So that's a 2m basically. So this is group 4 bar 2m. Finally, we can say what's a 2, 2, 2 plus an inversion center. And almost by inspection by now, you should remember what we talked about, which is that, well, the 2, 2, 2 all is a pi's, And if I do inversion, I'm going to end up with mirror planes. So what that means is that obviously it doesn't matter where I start. If I take the 222s that are available in our, sorry, take the twofold axis available in the 222, right? And I put in an inversion. What this means, as we discussed before, is that automatically is going to put in. So let's take the one I'm looking at, right? It's got an inversion. It's twofold axis. That means that perpendicular to the twofold axis, I have a mirror plane there. For this one, looking down this side, it goes through an inversion center, so it's going to have this one, and the same for the other case, right? I've drawn it in perspective here, right? But so that means that this is essentially 2 over m, 2 over m, 2 over m again. So nothing unique there. So now if I come and look at our table, and I look at the 222, when we added this horizontal plane, we got a new one. Right, so again, going down on a 222, I add a horizontal mirror plane, and I got a new one. It was 2m over 2m over 2m. I have perpendicular to every twofold axis, I have a mirror plane. When I added a vertical mirror plane, there wasn't any difference. It produced the same thing. When I added a diagonal mirror plane, I get another diagonal the other way, using the 2mm theorem here. And when I look at what it does to the motif and everything else, I end up with a now transforming this twofold axis into a roto-inversion axis of 4 bar, and each direction has a mirror plane and twofold axis, and so it ends up being a 4 bar 2m. So in the next lecture we'll do the same thing, and now we're going to take 3-2 and we'll proceed down in this direction.